All right, today we're diving into a really revolutionary idea in computing. It's an approach that's all about teaching machines to think a little more like us, with all our beautiful, messy human imprecision. Welcome to the amazing world of soft computing.
Just think about this for a second. How can a machine, something that lives and breathes in a world of absolute zeros and ones, possibly grasp a concept as subjective as warm? I mean, is it 25 degrees? 30? What if there's a breeze? This is exactly the kind of fuzzy, real-world problem that soft computing was built to solve.
To really get it, you've got to look at its opposite, hard computing. So on one hand, hard computing is what you probably think of as traditional programming. It demands precision, it needs exact models, and it follows a super strict set of rules, no exceptions. But soft computing? It's designed to embrace ambiguity. It's totally fine with approximate information, it has a really high tolerance for uncertainty, and, this is the big one, it's adaptive. It actually learns from the world around it.
So what is soft computing really? Well, it's not just one single method. Think of it more like a specialized toolbox, a partnership of different techniques all working together. And this toolbox is designed specifically for those messy, complex problems that are just too much for the black and white world of traditional computing.
Now, the three main tools you'll find in this box are neural networks, which are fantastic at learning, fuzzy logic, which is brilliant for reasoning with vague info, and genetic algorithms, which are used for optimization. For our explainer today, we're going to zoom in on the two heavyweights, neural networks and fuzzy logic. Okay, let's kick things off with a tool that has absolutely revolutionized artificial intelligence, neural networks. And their inspiration? It comes from the most powerful computer we know of, the human brain.
An artificial neural network, or ANN for short, is basically a system designed to mimic the way our own brains analyze and process information. It's made up of this huge network of interconnected little units we call artificial neurons, or nodes, and they all work together to make sense of data.
And the basic building block for every single one of these massive networks is this little thing right here, the perceptron. It was introduced way back in 1957 by a guy named Frank Rosenblatt, and it's the simplest possible form of a neural network, just a single artificial neuron. Seriously, think of it like the individual Lego brick from which all the massive complex AI we see today is built.
And this gets to the absolute heart of what makes neural networks so powerful. They don't just follow a fixed program. They actually learn. They make a guess, they see how wrong they were, and then they adjust their own internal wiring to do a little better next time. And they do this over and over and over again. So you might be asking, how in the world do they actually do that? Well, the magic behind this self-correction is an incredible algorithm called backpropagation. It's pretty much the standard way we train most artificial neural networks these days.
All right, let's break down how this learning loop works. First, the network gets some data and makes a prediction. Step 2, it calculates its error. Basically, it looks at how far off its guess was from the right answer. Third, and this is the genius part, it works backward from that error and adjusts the weights of its connections. You can think of these weights like thousands of tiny volume knobs. The network turns some up and some down, trying to tune itself to get closer to the correct answer. And finally, it just repeats this loop, thousands, even millions of times, getting a little bit smarter with every single cycle until the error is as small as possible.
Okay, so neural networks are amazing at learning patterns from tons of data. But what about problems where you don't have massive data sets, but you do have human expertise? Well, that's where our second tool comes in. We're going to shift gears from learning to reasoning with something computers normally hate, vagueness.
At its core, the mission of fuzzy logic is pretty simple. It's a translator. It takes those imprecise, experience-based human ideas like, hey, it's getting a bit chilly in here, and turns them into a concrete set of rules that a machine can actually understand and act on.
This quote really highlights a crucial difference. See, knowledge is a hard fact, like the temperature is 45 degrees Celsius. But experience, that's the understanding that 45 degrees means, wow, it's a very hot day. Fuzzy logic is designed to capture that kind of experiential wisdom and build it right into a machine's brain.
So how does this actually play out? Let's use a smart heater as an example. It all starts with a precise, or what we call a crisp, input, like the temperature is exactly 14 degrees Celsius. First up, in a step called fuzzification, this number is converted into a general concept, like cold. Next, an inference engine, the brains of the operation, applies a simple human-like rule. If the room is cold, then the action is to heat. Third, that fuzzy command, heat, gets defuzzified, meaning it's translated back into a very specific instruction. And that leads to the final step, a crisp, clear output, like set the heater to 28 degrees.
You know, you might be surprised by how often you're already interacting with fuzzy logic. It is the hidden smarts in so many devices, from the air conditioner that adjusts cooling based on how hot it feels, to the washing machine that changes its cycle based on how dirty the clothes are, all the way to advanced systems in cars and robotics.
So at the end of the day, when you combine the data-driven learning of neural networks with the common-sense reasoning of fuzzy logic, you get soft computing. It lets us build intelligent systems that can actually handle the nuance and the uncertainty of the real world. It gives us a way to solve problems that are just totally out of reach for rigid, traditional code.
It really makes you wonder, doesn't it? If we can actually teach machines to master something as fundamentally human as ambiguity, what's the next great frontier they're going to help us understand? What other complex, messy problems are suddenly within our grasp? Thanks for tuning in.